How's it going, everyone? Welcome to another video. Euler Gonzalez here. Right now, we are going to look at this particularly course of rethinking asynchronicity in JavaScript. Why this is important, you may wonder. Well, because it all starts by understanding is now this advanced Redux or this specific middleware in Redux called the RTKey as a way that the problem that this library solve or this middleware solve is that it requires less ceremony when it comes to define and build the update logic or this state update logic, provide you much more better TypeScript support, and you can now add middlewares without the hassle and without needing to look at Google's and that kind of thing. And also it come up and provide you some features that make asynchronous or side effect much more convenient and appealing. So this async aspect here, as a way to understand now how you can create your own Redux, by the way, and understand what is the value proposition of Redux, we need to look at the Redux fundamentals here. So because at the end of the day, this is, well, a well-battled test state management that not only works for client-side application, but also for server, any JavaScript environment, where the idea here is to first make the state update logic maintainable as a top priority. How? By using the Flux architecture to do that, and by defining its action, which is part of the Flux architectures, we're going to make those actions in a semantic, meaningful way. So to do that, we need to use some sort of these functional programming concepts such as purity, immutability, partial application, current, as well as monad, as a way to understand now how we're going to make that happen, to update the state in a consistent and maintainable way. Therefore, that's why we have our reducer, which is the update logic. We're gonna use that as a way to now understand what is the data flow and the update logic. So this Redux, this state management is important to keep that state management API as small as possible and extensible. Because the end goal of that, this is the intent that I described. Because the end goal is to, using the Flux architecture as an inspiration to make the state management mutations maintainable, and that is anytime you want to actually update your state, you have to do that synchronously. And if you need asynchronous behaviors to perform side effects, so it can be human or computer inputs. Human inputs like typing an input or scrolling into a page, or just to mention a few ones, a computer like waiting for this image to load in the browser, or fetching data from the server. So if you need to achieve this particularly side effect, put your logic aside, separate from the act of updating that. So we can now use these reducers, this piece of updated logic that is going to be handled as one state, one piece of data, and we can compose that into a single store rather than multiple one, which is something that Flux recommended. So with that, we can make our application much more easy to test, to debug, and to persist that state. So all of this is just based on also the Mark's fundamentals, especially on the Tao of the Redux. There is a very nice article where he described about this design principles and intent, as well as the goal, right? And as a way, we started to look and dive deep, how can we now create this Redux from the scratch, which is, after all, is just a simple object that has several functions attached to that. We started to explore now is what are part of this API that Redux expose. So for example, compose, right? So what compose allows to, which is now these nice little functions to trigger functions, and the output of that function will be the argument of the next one, and so on and so forth. So here we are not able to pass some arguments to that functions. We just only is calling that function. So we're gonna let this particular compose functions actually call that. So we started to also look at, well, how can we create now is our store, which is another piece of the API that Redux provide, and that is now a particular object that has let me see. Well, this is a particular object that have these particular shapes, which is the dispatch, the subscribe, the replace reducer. We look at what each one of them is doing, which one of these functions are actually doing. So this is dispatch, you're gonna pass an actions and then get state as a way to get the latest state of that. Replace the reducer, as their name suggests, right? As well as subscribe. It's like, hey, I want you to now listen to this particular state when that change. So we started to see how can we now create these actions from the scratch, start using is now the Flux architecture as a way to see how we can create now all the necessary things to update our state, which is creating an actions, which is an object. How important it is to create a function around that as a way to test that. That is known as the create actions, and then how we can now bind those actions to our store, and instead of actually calling that dispatch actions, we just only use this particular actions creator, which behind the scene must be used is the compose functions as a way to now call that action functions and then pass that as the input to the store dispatch, right? So the idea of using this bind actions creator is that we're gonna get all of this name actions, and we simplify the process of calling that function and then pass the action, and so on and so on and so forth, right? So we make it much more meaningful. And also another part of the API is the compose reducer. So this is pretty straightforward. It's like, yeah, you want to now make all of this update logic maintainable, and you then attach then all of this to this single root reducer, where inside of that you're gonna define which state you want to update or you want to interact with. So far so good. We also look now at another important thing, which is the enhancers. This is now give you the ability, so that enhancer, after all, this is a current function. So enhancers, after all, is just give you the ability to now add or change functionality to the Redux store, to the core. So for example, here, this is widely used in development tools. So for example, React DevTool is now an enhancer, is now a current function, is now a specialized function that the current and the partial applications is just techniques of specialized functions, where now the partial application, you preset the arguments first, and then in the next call you pass the rest of the arguments. Where now on query you say, no, we're not going to pass the initial value, we're not going to pass any initial data here, and in fact next call we're going to now pass one argument at a time. So it's say one input, one output. That'll be the arguments of the next function. You say one input, one output, one input, one output. There is also things known as loosely coupling, where this is when you this is what you're gonna find in a lot of JavaScript variables, especially because this is much more convenient, and that's one of the reasons why we use is partial application, or the functional programming that wrote and continue to write in this kind of libraries actually are doing. So that's great for enhancers, and then we also look at middlewares. This is just enhancer, and then we look also is at middlewares, where now middlewares here allows to intersect is actions. So these middlewares intercept actions to add behaviors between the dispatch and the reducer, right? This distinction is something important because this will lay out the foundation of then how can we now is adding asynchronous behavior. So how can we now is dealing with this side effects, network call, or waiting for an image to load, or user inputs, scrolling. So any interaction that we need to wait, any side effect, any part of the program that modify the data structure or the variables or data that come from the server is what we're gonna put here. And you may wonder, is like, how is the things work? How this asynchronicity works, especially when you're writing these functions. How asynchronicity works in the language, And what is asynchronicity for the language? This kind of definitions is something that when you started to do challenge and lead code, is quite important to know that, because this will lay out the foundation of how you can design a solution for a problem, right? So this particular case, we look at how can we create is our log middlewares, as well as performance middleware or timing middleware, monitoring middleware. But the idea here is that they only trigger on like enhancers, where they trigger when the story is created. Middlewares are triggering on every dispatch process, because it allows you to intersect behaviors between the dispatch and the reducer. So here you can check when so it runs between the dispatch process, which means that before and after the reducer, and you can change multiple middleware as you see fit. So here you can add now several of this functionality. The most common use case is like log the customer behavior when navigating to a page, or adding to or connecting to a so performing side effects like routing, so logging actions, as well as you can now turning an async API calls into series of synchronous actions. What does it mean is that here is when you're going to define is your asynchronous behaviors and then turning into a series of these synchronous actions. Again, the key word of this is that how now a synchronicity is handled, and what is a synchronicity for the language, for JavaScript. So we looked at there is a widely common middleware called Redux that actually handles this particularly Ajax requests. Okay, so this is a famous use of middlewares in Redux RTK, where it say, hey, let me actually intercept these actions and then run the Ajax, okay, or fire the promise or Ajax requests, and then fire the real actions afterward. So that's this story that we are creating here, this narrative that we are telling here, is crucial, especially when it comes to understand where this asynchronicity comes here. And here we ask ourselves, what is a thunk, right? Yeah, we ask, what is a thunk? You know, we ask ourselves, what is a thunk? Before that, and I will argue this. So before understanding what a thunk is, we need to know. We need to know. We need to know what is a synchronicity in the language. Okay, asynchronicity, exactly. Before understanding what a thunk is, we need to know what asynchronicity is in the language. Okay. And before understanding what a thunk is, we need to understand what a synchronicity is in what is a synchronicity in the language, and how that works. That's why we're looking at this. You know. The fuck that? Okay. Exactly. It's like, what's a thunk? But before understanding what a thunk is, we need to know what a synchronicity is in the language and how that works. Because this is now not only how we're gonna here we're gonna look at how we're going to handle is this kind of complexity in our applications. So as JavaScript applications, this is where the value will come here, and we need to understand now this particularly async patterns, async problems that happens in some of the typical solutions patterns when we are writing our JavaScript applications. And that is something important, because by understanding these particular patterns and in the conceptual understanding that, as well as with practice, why we do the thing that we do, a lot of the time it will give us an insight of the way how we doing these kind of things, and as a way to solve these particular problems and see when can we use now these patterns when dealing with this asynchronicity nature, this nature of building now modern web applications that are not only is running or programming is synchronously one line after another, which is after all what JavaScript is, but also what happens when we need to deal with this a branch situation, when we need to wait for this data to be low. So that's why here we're starting to look at what is parallel and async, right? So parallel, you can think of this like when you go to a Six Flags and a particularly parade or an attractions, you say, or a roller coaster, you say, oh, good, right. That entries may have is 30 lines in which they can now handle this massive, where they can handle now is 30 peoples at the same time, right? So this is now parallel. In true parallelism, in our brain is something, or from the cognitive perspective, is something that we're not going to see because I'm not a neuroscientist, but unlike biological things that need to happen every single second to keep us alive, cognitively, even though that we talk about that we are multitasking and we can do several things at a time, we are not truly multitasking, we're not truly parallel, right? Not from the cognitive perspective. So this is why now computers, processors, where they have several of these threads of this queue, pretty much like the Six Flags attractions, roller coasters, you now have is depend on the type of processor, they can have now 8 or 16 or 32 threads where they can now is work, where they can now put all of these tasks and deal in them at the same time. So if you can imagine this particular task having 30 threads to handle in tasks is not enough to actually run as a OS, not to mention the browser, right? So because of that, as you can imagine, so writing a browser is something that is not trivial. So for example, Firefox actually have more than 31.5 million line of code. You can guess why. In this, even though the processors have these virtual threads or these logical threads as a way to handle with more load, as a way to delegate all of these tasks that it can manage and schedule them. So as a developers, you just give the things, as a developer, you just give that by settle. Okay, as a developer, you just give this. Yeah, as a developer, you just this. As a developer, you just give the things. Jesus. As a developer, you just give the things as by settle, right? So you don't have to worry about with parallelism, performance, and things related to that. So for example, taxes and semaphores. That's quite wild, bro. Exactly, but so what I'm doing here is just creating this narrative, right? This narrative that is just asking questions. So we started here to look at what is asynchronicity in the language, what is the subtle difference between parallel and async, and how parallel is pretty much like you have when you go to a Six Flags or Disneyland and you want to get in one of these roller coasters, when you have all of these different queues, and they can now attend 30 people at the same time. So now we're talking about that. So this is parallel, true parallelism, and when people started to align to, or when people started to accumulate in that, so now you have to wait until this next person, until the persons in front of you can now actually pass it, right? So the thing is that we can now, this in the sense of the attraction, this roller coaster can only deal is with, for example, 30 people at the same time, right? And similar to when they get into this particular roller coaster, they can, so 30 people, let's say they have 30 seats in that attraction, so only 30 people can actually experience that. And then we have now these things where people exactly to now putting one after the other, right? The idea here is that in the context of processors, that's what we have now threads. So threads, some of them can have 4, or 8, or 16, 32, right? As a way to deal with this kind of task at the same time. So that is true parallelism. However, if you can imagine, 32 threads is not enough, especially to run. It's not enough for run a browser, and especially to run an OS. So that's what we have now. This virtual or logical threads, where we can handle more load and delegate tasks, delegate and schedule tasks. So when it comes to now the asynchronicity, the word asynchronicity, okay, where the idea here is to run all programs, in our case JavaScript programs, okay, on the browser, that the browser use multiple threads, we can now run our JavaScript programs in a single thread, which means that per instance you are running exactly, so per instance or per thread you are running one JavaScript line at a code in the JavaScript engine. So the JavaScript engine is now running is one line out of code per thread. Okay, so in theory you can spread all of this JavaScript instance in multiple threads, so you can have, what you can simulate is parallelism. The problem is that in each one of those threads they can communicate. So the problem with this, in each one of those threads, the problem with running this, at least from the computer perspective, the problem with this thread is that they can't communicate each other. So that's why we have now web workers. We're trying to close the gap between that, and as a way to now create a separate threads where you can now share data across all of these different instances. However, this is now platform specific. This is not a JavaScript thing, right? So we as developers, that's good news. Yeah, that's good news, because we as a developer, we don't have to worry. Yeah, we as a developer, we don't have to worry about parallelism. And all of the crazy stuff that people that work in there actually handle that. So for example, like tags and semaphores and log communicating and resource locking. And they say resource locking because this is something quite interesting. Resource locking. this resource locking, I'm assuming that if you are dealing with parallelism, share resource locking, on share resource, the lock statement, ensure exclusive access to share resource. And this is for C#. But this is for multi-threading. Distribute locking, ensuring consistency in shared data. This is in multi-threading. The lock statement. Java multi-threading locking strategy. The concurrent. And this is okay. It's very interesting. So yeah, the idea of using now threads, this concept of threads, is because on these threads is where now a program, all of these sentence, all of these statements will be executed. That's what they call these threads, right? And on each one of those threads, which is now where a program, a JavaScript engine is now running one line of code at a time, they can communicate with other ones, right? With other threads. So that's why we have, as a way to recap, is this web worker, which is now another thread that is created to close the gap between them, to communicate, to share resources. So, but that's not a JavaScript thing. That is a platform-specific thing. And the good news is that we don't have to deal with concurrency and all the wild things that can happen there. So, for example, taxes and semaphores and resource locking. Okay, and this gave us now, as a JavaScript developers, is the process of now communicate with other the process of communicating with other threads through asynchronous events, using now the event loop notions. So this particular notion of the event loop and the asynchronicity in the language, and especially the way how now in JavaScript we need to deal with asynchronicity, is with this thing known as concurrent, with things people have different meanings about concurrency, but the idea here is that instead of looking at this as all of the tasks that need to happen at once, unlike parallelism, concurrency is now multiple tasks that overlaps in time. So this cognitive notion is that we now are concurrent when we are dealing with tasks. So for example, because we are writing our application in a single thread, and as a way to handle asynchronicity, we use the event loop notion. And this asynchronicity is not that things happen in parallel, right? Is that the task overlaps over time. These notions, these notions is what cause the vast majority of the problems. Why is that? Because when you need to provide solutions to this, to business, and let's say you are now, and I think this is a very good example. And let's say now you need to, you're working for a company that actually are selling TVs to celebrities, right? So you are selling a TV to Kanye West. So you say, oh, good, cool. Now you design your applications. This application is your UI, and then the endpoint, the APIs. You make everything to look appealing to the users and also usable, which is great things. And then by the time that is actually the requirement, which is on the checkout, all right, let's say you use now a third-party library for that. This is a warning tale as well. And that third-party library that you're using now as a way to make this HTTP request and handling is that kind of thing. What happened is you set that up, which works very well. You deploy that, you run before deploying, you pass through your tests. Your tests already passed. You put that in a staging environment. It also works well as expected, which is great, good. And then, well, that's it. You suddenly receive a call from your CEO at Saturday 1:50 a.m. Telling you that the application, the Canny is now complaining about ourselves because they get charged 5 TVs where he only ordered once, and even though that we can pass through this process with the credit card and providers as a way to reverse those operations, the idea here is that we need to find a way what that happens and how to prevent that. So then you go and take a look at your code. You're right. You do the proper analysis. You realize that you are using is this third-party libraries. That when you see here is like, hey, the way how it's handling is this network call, is asynchronicity as a way to send the checkout object to the server and then wait for the response. Is something that is being done quite weird. All right. And this is causing the source of the problem. So then you go to your CEO, and the CEO says like, yeah, that's great, cool. So yeah, then you go back to your CEO with this new, and no CEO actually is going to be happy if you tell them, hey, that's not our fault. That was the third-party library that we were using that caused the issue. We already in contact with their support as a way to help them to fix that, and yeah, so that will never happen again. Your CEO won't be too happy to hear about that, especially because you as an engineer, you know that you must have to handle that particular thing, and you must know the tool behind that itself, right? So, all right. What is the cautionary tale of all this? Is that the moment that the JavaScript, the moment that we are diverged, the moment when we diverge is our cognitive perception of writing code from the JavaScript engine. That's where the bugs happen. And this is something especially true for concurrency. You know, or which is this particular notions of that. So let's get in today's video, explore more about this notion of concurrency, right? Why is this? Because remember, at the end of the day, we need to know how our tools work, one, and second, how to handle this now, these specific areas of responsibility here. So not only to write the code, in the case of the UI especially, it is not only the ability to manage the data, but also to how to communicate with your APIs, and how you can deal as this complex user interactions, as well as the asset management. So this particular section that sits between the data management and the complex user interface, where the idea here is that how can we handle this async operation with this concurrency, because at the end of the day we are getting paid for handling is this kind of complexity. So not only the ability to make our code, not only the ability to build and design a system, a UI system, for example, in my case, not only the ability to design a UI system, but also to maintain that, as well as to manage the time complexity or the concurrency here, this coordination that needs to happen. So I'm gonna make a quick pause here because Capitalist has shown that is very, so Capitalist has shown for us that it is very, very good to make us to coordinate ourselves. So this capitalism has provided an incentive as humans to now organize and coordinate us and our research way much more better. And you like it or not, this is something important. This is what has bring us to this moment. Huge thousands and thousands of previous generations actually know their way through, not only to fight but also to pass their seats, and while they're doing that, find a way to survive and thrive. And one of those is when you're able to manage your research in an effective way. So the more effective you are to manage your research, the more you can now impose or to control is the outside nature. This is also interesting. I will argue that the more you can now is to coordinate, schedule your own yourself, the better off will be as a way to dealing with others and to deal with nature. So this is another reason why I'm actually recording this series of videos, and as a way to make this as a social proof of work. All right, so by the time that other people have their own chaos, okay, I can see it, particularly at the front-end applications, I can see it, all of their mess, and provide their value, charge them, and move on, right?
It's fundamentally what the event loop is. Right? It's not like your response callback gets to interrupt and say, oh, it's time for me to run. They call it in JavaScript. At any given instant, it's only doing responses happening concurrently with the repainted, even though at any given instant, only one of those micro-level tasks is occurring.
Another thing is that the browser is a single thread as well. So for example, the critical rendering pass is happening in one single thread, which is the UI thread. And that is the main thread as well. So if you block that operation, of course, you're going to slower pages, as you can see. Exactly.
Repainting your page, it tried to do that, but at that exact moment, something else was running. So it had to wait in response cycle. Fire off a request, we get a response back. Now let's pretend that the blue represents the scroll, green color, and it's broken up into two things are happening at the exact same instant. I would describe concurrency as two higher level tasks happening within the same time frame. So rather than an instant, we're going to look at a time frame, and we're going to say concurrency as two higher level tasks happening within the same time frame. So rather than an instant, we're going to look at a time frame, and we're going to say within this time frame, two higher level operations are going to occur. To understand the notion of higher level items or higher level operations occurring, we also have to understand that higher level, or what I might call like macro level tasks, can be broken up or thought of as being broken up into micro-level tasks. So here's a way to visualize the macro level and the micro level and how these things might go together. So on the left-hand side, we have this yellow-orange task, or the macro-level task, which is broken up into those individual numbers, 1, 2, 3, 4, which would be micro-level tasks. These are my made-up terms. These aren't official terms, but macro-level and micro-level tasks. Okay? And then on the right-hand side, we have another macro-level task represented by that blue-green color, and it's broken up into 3 pieces, 1, 2, 3. Now, for the easiness of math, I'm going to pretend and assume that each one of these micro-level tasks takes 1 full second to complete. So this overall system, to do all of the tasks, it's going to take 7 seconds. Does everybody agree with that? Because it's a single-threaded system, nothing can happen at exactly the same moment, so those 1 second micro-level tasks are going to have to be...
Yeah, does everybody agree with that? It's like in this particular case, it's like, yes, all of this particular tasks, micro tasks and micro tasks that need to happen at the same time frame, instead of parallel, instead of instance, because this is now the subtle difference between the parallelism and the time and the concurrency, is that with parallelism are things that can happen at the same, things that can happen in parallel in the same instance. So things that can happen in parallels per instance, right? So instead of looking at the instance, it's looking now at the time frame. So things that can happen, or high-level tasks that can happen, high-level tasks, or in this case is tasks that overlaps over time.
Scheduled in some way that all 7 of them finish, and that's going to take 7 seconds. Let's pretend that the yellow-orange represents an AJAX request and response cycle. Fire off a request, we get a response back. And let's pretend that the blue represents a scroll, that we scroll on the page and it repainted everything because we scrolled to a new location on the page. These two operations have to fundamentally happen on the same thread. The entire user interface of our browser is happening on the same thread. So our JavaScript, the garbage collector, the style engine, the repaint, everything, it's all happening on one thread.
Everything of
which means we kind of have to worry about contention. And if you've ever had an animation on your page have jitter in it, you know why that happened? Because something contended on the UI thread. At that moment, your CSS engine was trying to, or your layout engine was trying to repaint the page. It's 60 frames a second way that it's repainting your page. It tried to do that, but at that exact moment, something else was running. So it had to wait an extra moment, and that's what created that jitter. Single threaded. So if we have these higher level, macro level tasks that we want to happen concurrently, I want the yellow and the blue to happen at the same time. Why? Well, let's imagine they don't. One way of scheduling this system, one way of scheduling this program, is to do all of the yellow first and then all of the blue. What would that look like on our page? Ignoring the 1 second thing for a moment, what it would look like on our page is that it would look like I clicked the button to make an AJAX request, and while that was happening, I tried to scroll my page, but everything was completely frozen while that happened. And then after it finished, then it sort of, jumped back and caught up. We actually have precedent for that. It's called synchronous XHR, synchronous AJAX. One of the worst evils perpetrated upon the web platforms. It's a terrible idea. There are people out there that are crying and literally complaining on standards lists saying, how dare you take away my synchronous XHR? It's been deprecated and removed from the web platform because it's a really bad idea. It's a terrible idea to schedule it that way, isn't it? Because even though the overall system would still take 7 seconds, that particular choice of scheduling those micro-level tasks would feel terribly inefficient. Does everybody agree with that, just from a user experience perspective? If, on the other hand, we chose to interleave these things together, where one...
Exactly. Because this synchronous HSR is like, that's not a good idea, especially if you put all of these tasks, if from the user perspective, it's not good. Because if you're putting all of this synchronous XRR or all of these tasks that can happen in a particular time, from the developer perspective, of course, give is much more control. But for the user perspective, it's like it breaks the user experience.
One thing might be blocking, so we can do something else while one thing is blocking before it can move on to the next thing. If we chose to schedule those things in an interleaved fashion, the overall system might still, in fact, take 7 seconds. But the perception of the performance is that things are going to be happening in parallel. Really, more importantly, we should be saying those things are happening concurrently. The AJAX and request and response is happening concurrently with the repainting, even though at any given instant, only one of those micro-level tasks is occurring. So, just to visualize that, my fancy animation took me about 2 hours to get right in Keynote. Here's a way of scheduling those micro-level tasks onto that single thread in the middle called the event loop. I don't know why that advanced. the single thread in the middle called the event loop. That's what we call it in JavaScript. At any given instant, it's only doing one of that single thread. Visualize that. My fancy animation took me about 2 hours to get right in Keynote. Here's a way of scheduling those micro-level tasks onto that single thread in the middle called the event loop. I don't know why that advanced. The single thread in the middle called the event loop. That's what we call it in JavaScript. At any given instant, it's only doing one of those things. So when you have an AJAX request that comes back and you need to fire the callback for a response, if at that moment somebody's already executing, nobody gets to cut in line. Right? It's not like your response callback gets to interrupt and say, oh, it's time for me to run. You know what it does? It gets at the end of the line, just like everybody else. So when the garbage collector says, I need to collect some garbage, and the style CSS repainter says, I need to repaint the page, and the layout engine says, I need to do some work, and the JavaScript engine says, I need to fire this response callback, and every single one of them, it's a first come, first serve, everybody gets at the end of the line. That is fundamentally what the event loop is. Okay? So that's just a high-level view to help you sort out what's going on. And the main point here is that the scheduling of this is not always entirely within our control. Sometimes it's race conditions that choose one versus the other happening. Not all of that's happening, but there's an awful lot of coordination necessary. Sometimes it's the coordination of when things happen, but oftentimes it's the coordination of responses to things happening. Because it's not always a very serial, like do this, and then when that's finished, do this, and then when that's finished, do that. Oftentimes it's much more complex, like, hey, go do these 3 things in parallel, and then when at least 2 of them have finished, you can move on and do this other thing, and then when that 3rd one comes along, you can branch out here and do this other thing. And before long, it's just crazy complex tree of different states of things that can happen. And it's that complexity that we have to manage in our programs. It's that complexity that begs for us to have better patterns for concurrency management. That's what asynchronous programming is, managing our concurrency. Okay? So that's a motivation for you from a philosophical.
Yeah, but this is a motivation move. Yep. This is a motivation for us, especially when we're dealing with this concurrency. And the concurrency, which is, at the end of the day, is this way of how do we handle micro task, okay, that happen at the same time. Okay? So how can we handle this macro task and micro tasks that happen? How can we handle this macro tasks and micro tasks that happen at the same time, right? Or in other words, how can we now make all of these tasks that are overlapping in time? And especially when you are writing this kind of application, let's say you want to communicate with the server, right? And then suddenly you now are receiving is the styles for this new page that you are rendering in the layout. So all of these particularly micro tasks need to find a way to be processed by the JavaScript engine, by the browser. But the browser, by design, is single threads. So that's why we have now this notion of the event loop, where this is now processing its task as it sees fit. So this kind of coordination is required, which is something that is now handled by the browser, and luckily, thanks for that. We need to understand is that how that things work, because we are going to deal with this kind of complexity, and that's why we require some sort of patterns, some sort of typical solutions to common problems.
Philosophical and conceptual basis of the motivation for why we go to the lengths that we do to try to write the programs that we do. Everything that I'm going to show you in this workshop is something that could fundamentally be done with nothing but the callback. There's no new functionality here. But we're going to see that the callbacks fundamentally are insufficient for expressing
everything every async pattern we are about to see can be achieved with the callback. But we are going to see that is insufficient. Yeah, but we're gonna see that but we're going to see that is insufficient when expressing that's insufficient when expressing code in JavaScript.
The higher and higher orders of complexity that our modern JavaScript program. But we're going to see that the callbacks fundamentally are insufficient for expressing the higher and higher orders of.
Exactly, that is insufficient for expressing the higher and higher orders of complexity we need to deal in JavaScript applications.
The complexity that our modern JavaScript programs are doing. Our modern JavaScript programs are falling all over themselves because we need these higher order patterns and we're not disciplined.
In our JavaScript programs need these high order patterns to make it work.
Higher and higher orders of complexity that our modern JavaScript programs are doing. Our modern JavaScript programs are falling all over themselves because we need these higher order patterns and we're not disciplined enough to.
Our JavaScript programs are falling behind because we need these high order patterns, and if we are not disciplined to apply them, and we're not disciplined to learn and apply them, then we're going to
learn them and implement them. We just keep doing the same thing we've always done because it always worked and it always worked and it always worked. This is a call to arms.
If we're not disciplined to learn and apply them, we'll continue to use things that work for the sake of work.
Say the new baseline of competency,
but not solving the problem.
Sophisticated, strategic, and tactical approach to your concurrency manager, to your asynchronous program.
So JavaScript developers. So the next level of JavaScript competency for JavaScript developers is to know this pattern, or is to have no strategicness.
Sophisticated, and it always worked. This is a call to arms to
So
say the new baseline of competency as a
system.
JavaScript developer is to have a much more always done because it always worked and it always worked and it always worked. This is a call to arms to say the new baseline of competency as a JavaScript developer is to have a much more sophisticated, strategic, and tactical approach to your concurrency.
So the next level of competency for JavaScript developers is to be strategic and tactical to deal. To be strategic and tactical.
New baseline of competency.
To be strategic and tactical to approach
sophisticated,
asynchronous
strategic, and
programming.
tactical approach.
So the next level of competency for JavaScript developers is to be strategic and tactical in your approach of dealing asynchronicity, or to dealing concurrency, to dealing asynchronicity, or to dealing concurrency, or your approach of management, to approach of concurrency management. To concurrency management in your asynchronous application. That's one of the reasons why also I'm looking at this, because I need this kind of tool. I need to be strategic and tactical when I need to be strategic and tactical to approach this concurrent application, this concurrency management. This concurrency management when writing asynchronous programs in JavaScript.
To your concurrency management, to your asynchronous program. We're going to look at some problems with callbacks. We're going to get some practice with them, and then I'm going to articulate to you the real essence of what callback hell is about. But I want to look at some issues with callbacks. So, easiest, simplest expression of a callback in an asynchronous fashion. We pass the function as a callback to another utility. This one happens to be built into the JavaScript engine, but it could have been some other utility in our code. We pass a callback in. Now, if we were to describe what this function does or how this function operates, we might say something to the effect of, set up a timeout, and then after 1,000 milliseconds, execute the console.log statement. Most people would probably nod in agreement. That's roughly how we would describe the behavior of this program. Unfortunately, that description is fundamentally insufficient. There's a deep deficiency there in our ability to understand and reason about and describe and articulate what's happening. So one of the issues that we have is that our brains are not actually working the same way that the code's working. But another thing to think about is that this function is oftentimes referred to as a continuation because there's a first half of our program and a second half of our program here. It may not be obvious to you, but the first half of your program is everything on the outside of the timeout, including the set timeout call itself. And the second half of your program is everything inside of the callback. In essence, there's a general concept of a now, roughly how we would describe the behavior. Describe what this function does or how this function operates. We might say something to the effect of, set up a timeout, and then after 1,000 milliseconds, execute the console.log statement. Most people would probably nod in agreement. That's roughly how we would describe the behavior of this program. Unfortunately, that description is fundamentally insufficient. There's a deep deficiency there in our ability to understand and reason about and describe and articulate what's happening. So one of the issues that we have is that our brains are not actually working the same way that the code's working.
So exactly, one of the issues with this code is that our ability to describe it is not sufficient. We can say that and that's exactly what happened to myself. When I started to see this, it's like, what the fuck is this? No. We can say that we want to run, okay? So we want to run a callback after 1,000 milliseconds, right?
But another
and here is when our code doesn't work, okay? And here's when our code doesn't work, and here's when our mind doesn't work because we don't know how our code works. Pretty silly.
thing to think about is that this function is oftentimes referred to as a continuation because there's a first half of our program and a second half of our program here. It may not be obvious to you, but the first half of your program is everything on the outside of the timeout, including the set timeout call itself. And the second half of your program is everything inside of the callback. In essence, there's a general concept of a now, the stuff that's going to happen immediately right now, and a later, for some definition of later. which we don't care about. We don't care what the real definition of later is. We just know it's not immediately after what I'm doing at the moment. There's some gap. And that gap could be a 0 millisecond delay, whatever that means. It could be waiting for an AJAX request. It could be waiting for a message from a web worker. Who knows? But understanding this notion of now and later, there's a first half and a second half. When we refer to functions as continuations, what we mean is we did the first half of our program now, and we wrapped the second half of our program up in a callback, and we deferred that callback to happen until later, and at that later moment, we're going to pick up and continue our program from where we left off. So that's where we get the term continuations for callbacks.
So callbacks are continuations.
How many of you have heard?
So that's why callbacks are called
Our program
continuations.
from where we left off. So that's where we get the term continuation.
The notion here is that this callback will be called at any time in the future. We don't know when, but it will. It can be a service worker. Interesting that you mentioned the service worker, man.
Pick up and continue our program from where we left off. So that's where we deferred that callback to happen until later, and at that later moment, we did the first half of our program now, and we wrapped the second half of our program up in a callback, and we deferred that callback to happen until later, and at that later moment, we're going to pick up and continue our program from where we left off. So that's where we get the gap. And that gap could be a 0 millisecond delay, whatever that means. It could be waiting for an AJAX request. It could be waiting for a message from a
It can be waiting for a message from a service worker or from a web worker, an AJAX request, 0 millisecond. Web workers, man. That's why it is called a continuation of the program at some point in the future.
web worker. Who knows?
Exactly. It's a exactly. That's what it's a continuation of a program at some point in the future. So that's what is callback here. Is that, hey, this is now a continuation of the program at some point in the future. It can be an AJAX request, or it can be waiting for an AJAX request, or waiting for a message from the web workers, or waiting 0 millisecond.
This notion of now and later, there's a first half and a second half. When we refer to functions as continuations, what we mean is we did the first half of our program now, and we wrapped the second half of our program up in a callback, and we deferred that callback to happen until later, and at that later moment, we're going to pick up and continue our program from where we left off.
As a continuation.
Continuations for callbacks. How many of you have heard that term callback hell before? I'm sure many of you will probably raise your hands in the online chat as well. Callback hell, it's one of those shared things, almost like we could have a counseling session about all the nightmares that we've had with callback hell, right? It's usually thought of as having something to do with this idea of nesting. In fact, sometimes it's referred to as the pyramid of doom because of that pyramidal shape, triangular shape to our code. But is that what callback hell really is? I think it's much, much, much deeper than that. I would go so far as to say, and this isn't intended as an insult, but I would go so far as to say there's an awful lot of my peers out there that have described callback hell as having to do with the indentation and the nesting. My response is I don't think you've thought very critically about what callbacks are really about and what callback hell is about. This is where I might differentiate from some of my peers in that I'm much more focused on the concepts here, even than the actual observations and the actual code. There's something conceptually deficient here. There's two conceptually deficient problems. I can start out proving to you that it doesn't really have anything to do with nesting and indentation by observing to you that this program does in fact suffer from callback L, but I can rewrite this program in a different style, sometimes referred to as continuation passing style. And this code is not nearly as obviously suffering from nesting and indentation problems, is it? We've used name function declarations rather than inline function expressions. Code does not in fact suffer from deficient problems. I can start out proving to you that it doesn't really have anything to do with nesting and indentation by observing to you that this program does in fact suffer from callback L, but I
So we can now is agree that this is something harder to read about this callback hell. However, we can write our programs. Okay. However, we can write our callbacks. Remember, continuations of our program at some point in the future. Okay. Like this.
I can rewrite this program in a different style, sometimes referred to as continuation passing style.
So hey, function 1, I want you to trigger this, that, and then this, that, and then this, that. And then what you can do is now calling those functions and pass that. And pass the function there. So by the time you pass now this callback, this continuation of the program, then after 1 second, you can say, hey, now 2, all right? Where now here, you're gonna pass this, hey, now 3 for that.
Proving to you that this program does in fact suffer from callback L, but I can rewrite this program in a different style, sometimes referred to as continuation passing style. And this code is not nearly as obviously suffering .
This code is known as the continuation program style.
But I can rewrite this program in a different style.
Exactly,
sometimes
continuation
referred to as
callback.
continuation passing style. To you that this program does in fact suffer from callback L, but I can rewrite this program in a different style, sometimes referred to as continuation passing style.
Exactly. This code is known as continuation passing style. But damn, so.
And this code is not nearly as obviously suffering from nesting and indentation problems, is it?
Exactly. And this code is not obviously suffering from indentation. Yeah, and this code is known as, and this code is not obviously suffering from indentation and callback. Yeah, it's not suffering from indentation.
Passing style. And this code is not nearly as obviously suffering from nesting and indentation problems.
From suffering from nested and indentation problems. Yep.
This is it. We've used name function declarations rather than inline function expression.
We use functions declaration instead of function expressions.
Does in fact suffer from callback L, but I can rewrite this program in a different style, sometimes referred to as continuation passing style.
We use
and this code is not
declaration.
nearly as obviously suffering from nesting and indentation problems, is it? We've used name function declarations rather than inline function expressions. If you look really close, you can still see the fundamental nesting going on, but we don't have that same pyramidal shape to our code. And most people that took a glance at this code would not naturally, instinctively think callback hell. But that's why callback hell needs to have a redefinition in our minds, because this code is every bit as susceptible to callback hell as the previous code. Even though the style looks different, it still has those same problems. We need a more nuanced, a deeper view of what callback hell is about. So we're going to do exercise 1, okay? Now, let me orient you to exercise 1, and it's really important that you get this orientation solid right now, because we are going to revisit this same exercise all the way through 7. 1, 2, 3, 4, 5, 6, 7 is the exact same problem domain, revisited in different asynchronous patterns. So starting out with exercise 1, let's open up the README in the ex1.js. Let's try to get more familiar with what this exercise is asking us to do. And honestly, what it's asking us to do is, I've attempted to articulate a pretty common pattern that we run into, especially in the user interface of our systems. What you're going to be asked to do is coordinate the responses to a set of fake AJAX calls. Fake AJAX, because I didn't want you to worry about setting up your own servers or any of that other stuff, so it's going to pretend to do AJAX. And I've got random delays in there such that every time you run your program, you're going to get different behavior out of it, just like you would in the real world. Okay? But these are fake AJAX. They're not actually making network calls, but it actually doesn't matter to us whether it's fake. What matters to us is that we want to pretend as if we're making calls and respond to the sequence of responses in a sane way. And the way we want to respond to that is, we're going to request all 3 of them at the same time, aka in parallel. We know we really should use the term concurrent. But in parallel, we want to make the same 3 responses at the same time, or same 3 requests at the same time.
Request all files at the same time in parallel. Render them ASAP. Just don't blindly wait for all to finish loading, but render them in proper, obviously, order. File.
When we get a response back from file 1, we want to print it right away. In fact, if we get file 1 and file 2 back, but file 3 is still waiting, we want to print file 1 and file 2 right away. We want to render them as soon as possible. Why? User perception of performance. If we waited until all 3 were back before we printed them, the user's going to feel like the system is slower, but if we progressively render whatever we have, they're going to feel like it's faster. That's a really important component of experience, is user perception. Even if it takes the same amount of time, the perception is important. But one additional wrinkle, which is I want to make sure that those files print in the correct order. So if file 2 comes back right away and file 1 is still pending, don't print file 2 yet. Wait until file 1 gets there and then print both of them. So what we're wanting to do is render ASAP, but in the proper order. You see there's a little bit of a twist here. And that's intentional, and that's a generalized statement of a pretty common pattern in user interface design, doing multiple things in parallel, waiting for them to come back, coordinating their responses, responding as soon as possible, but making sure things happen in a sane order. That's what this exercise calls for you to do. So let me orient you to ex1.js. You'll notice I have my fake AJAX. It's mapping from a URL like file 1 to some contents, and I've got some random delay in there. I've got an output utility, which is a convenient wrapper around the console.log for you to use. Here's my get file function. It makes that fake AJAX call. And this is the part where you need to start figuring out some code, because it's pretty easy to call get file 3 times in parallel. I gave you that for free. But the question is not how to coordinate the requests. The question is, how do I properly coordinate the responses?
Exactly.
And here's some hints for you.
The question is that how do I coordinate the proper responses, not the requests.
Have responses coming back because of the randomized delays. You can have them come back in any particular order. Some of them might come back too early, which means you're going to need to have something hold on to some state for a while. You're going to need some sort of global variable or object or array or something to hold on to responses in case you're not ready to print them. And you're going to need to figure out how to have all these callbacks sharing over that, or coordinating over that shared state, and figuring out when it's okay to print something and only printing it once. All right, so we're going to take about I said 5, we'll take 10 minutes because I want to make sure everybody plays around with this. We'll take the 10 minutes, and then we are going to take an afternoon break after the 10 minutes. So we will come back, talk through the solution, and then that will be the time that we take our afternoon break. But I want you to play around with the pain of callbacks, if you will, by understanding just how hard it is to do what should be sort of a simple use case. It's actually pretty difficult when you have to manage all that state yourself through callbacks.
Absolutely, bro. Absolutely. Okay. Absolutely. Okay. Okay. We need to learn from that. Okay. Okay. Okay, so let me actually create now a code pen here. A pretty simple index, you know, it's like a very simple index. What I want is to now is say something like this. I want to create a new one, plain JavaScript. Index HTML, yep. No, plain JavaScript, which is now asynchronicity. I want to make it public, right? Yeah, let's get into this. And then, right, I want now to drop this thing here. Wait. What the fuck you think you're doing? Oh, you think you... Man, what are you doing? There, you got it. Okay. All right. Let's get into this, right? Okay. So the idea here is to actually find a way to store that data, right? Which is get file, right? You can say get file. What is get file? Oh, as a way to call each one of them, right? As a way to call each one of them. So here we'll need is to, because at the end of the day The exercise here. Oh, the README is this. This exercise calls for you to write some async flow code. To start off, you will use only callbacks. Request all three files at the same time in parallel. Render them ASAP. You just blindly wait for all to finish loading, but render them in proper, obvious order. File 1, file 2, file 3. After all of three are done, output complete. Okay. So we can think of this as requests all three files at the same time. So trigger all of this response in parallel, and then render them ASAP, like this. All right. Render them ASAP. Just blindly wait to finish loaded. So one way we can do this is by saying, hey, let's go to define here. Anytime we call this get file fake Ajax, all right, we would like to now store some sort of state here. So anytime we call this, request all files at once in parallel. So for that, we will need to have a way to store this as a closure by saying it's like, hey, let me now define this as the this is now. So anytime we call all of this, request all files at once in parallel. Okay. So here we will need to have some sort of states here, where every time we call these functions, we can now store that, right? We say this is now the files here as an array, and where we're going to store each one of them, and this is when we're going to call is the fake Ajax, right? So here, after you're done, okay, so after you are done, because the first time it's gonna call the files 1, the second time it's gonna call the file 2, the third time it's gonna call the file 3, right? So we need somehow to, anytime we call this, anytime we call this, we request all files at once in parallel. Because what we really care about here is the response and how to deal with this response at once. Dealing with the response. Dealing with the response. So how can we manage is dealing with this response? Okay. So we can say, hey, we would like to now return this. We can create this a closure here, okay, as a way to run this function. Okay.
Let's talk through how we might choose to solve this problem. When this callback is called, we're going to get a response back, and because of closure, we're going to know which one of the three files it came from. Does everybody see that?
So this is per file.
So what I could do is I could have a handle response function that I call out to with the file name and the text that it got. Okay. Now I could do that code directly inside of here, but I'm pushing it out to another function so that I have a little bit less nesting going on. All right, now handle response receives a file name and some contents for the file. Everybody following that? What I'm going to do is need something in enclosing scope, in this case probably the global scope, some variable, some object that is going to keep track of the responses that come back in case I get a response back earlier than I'm able to render it. Everybody with me on that? I might get a response back and be able to immediately render it, but I'm going to need something to hold on to the responses that I get back that I can't yet render. And I'm going to need to be able to basically iterate over that collection of responses when it is time to print things out and print out whatever I've gotten. So the way I'm going to do that is simply have a variable called immediately render it, but I'm going to need I get a response, probably the global scope, some variable, some object that is going to keep track of the responses that have come.
It's because I need some variables to keep track of this.
In case I get a response back earlier than I'm able to render it. Everybody with me on that?
Yep. We need to keep track
I might get a response back and be able to immediately render it, but I'm going to need something to hold on to the responses that I get back that I can't yet render. And I'm going to need to be able to basically iterate over that collection of responses when it is time to print things out and print out whatever I've gotten. So the way I'm going to do that is simply have a variable called responses. And I'm going to make it an object. This is not by any means the only way to solve these exercises. That's with almost everything we do in these workshops. There's many different ways to slice it. I'm only walking you through one way of modeling this mentally, okay? So handle response could say if responses
this is a global variable
of file name, that is an object whose property is the file name, the URL that's used. If that's not already set.
Already set.
So maybe I would do that instead of responses of file name. Maybe I'll say, if not, file name in responses. So I make sure for a fact that this function.
So if file name is not in response, which is a great thing to actually check if this key is to actually check if this property is on this key.
Is getting called with a response that I haven't yet seen. Just takes care of maybe the function somehow getting double called or whatever, right? So I'm going to make sure for a fact that this function is getting called with a response that I haven't yet seen. Just takes care of maybe the function somehow getting double called or whatever, right? So I'm going to say this is a response that I have not yet seen yet. So the first step is definitely to add it to my object. I'm storing it into an object, okay? File name being the property location on the object, contents being the value that I'm putting into the object. So if that was file 1, if this was the first time this was being called and that was file 1, I could iterate over the stuff in responses, and if there was stuff to render, I could immediately render it, take it right back out of the responses object. Or I might have just put file 2 in and file 1 isn't yet there, in which case I can't go on yet. I just need to leave it there and try it again. I could iterate over the stuff in responses, and if there was stuff to render, I could immediately render it, take it right back out of the responses object. Or I might have just put file 2 in and file 1 isn't yet there, in which case I can't go on yet. I just need to leave it there and try it again later, okay? Keep in mind, this handle response is going to be called all 3 times. It's going to be called every single time we get an AJAX response back, it's going to get called. So it's going to have an opportunity to be called for all 3, but we're not sure which order.
So we have an opportunity to keep track of this and having this global variable. Not a good idea, but again, this is one of the solutions for this.
6 different ways that this can happen, or 3 different ways, or whatever. There's a lot of different ways that this can happen, and we're not sure which order it's going to happen in. So we are trying to coordinate that or normalizing that concurrency. So after I've made sure that my response has been stored into my responses, the contents have been stored in the responses, now I could simply start out
now
with an
can
array.
I say, hey.
Now this is a simple cheat way of doing it. There are, of course, other ways where I could have kept those in a external location in some way, but I'm just trying to come up with the simplest way of solving this problem. If I know what those URLs are and I know what order they're supposed to happen in, I could have produced this array by the order that they were requested in, if that's what I wanted. Again, just taking the simple way. Let's assume that I know that file 1, file 2, file 3 need to happen in this order. So now I can just say for var I equals 0, I less than arr.length, and maybe instead of arr, maybe I'll call this file names. I++. So I'm going to look at file 1. It's going to be file names of I, which the first iteration, it's going to be file 1. I'm going to say if that is in the responses object. So file names of I is in responses.
So if this is in responses as a key, because we actually is storing that as a key,
or it's not in responses. Can anybody guess what I'm going to do if it's not in responses?
so because what you want to do here is to key. Okay, so this will get triggered is 3 times, right? However, because we want us to now have a way to keep track is the response. That's why we create these global variables there. Let's say, hey, yes, let's go to keep track now all of this response here. If that doesn't exist, please add it. Okay. And any time we want is to now run this function. Okay. We also want is to here is iterate through all of this file name as a way to make this a static solution. Is a way to iterate through this object, check if that object exists, as a way to print that out. Okay. However, if not, if we don't want to, if that response is not, then we'll need to call handle response again. Or then we need to call this
break the for loop. Actually, in this case, for convenience sake, I'm just going to return. Just completely empty out. So whichever case I'm in, whether I'm looking at file 1 and it's not in there, or I'm looking at file 2 and it's not in there, or I'm looking at file 3 and it's not in there, I got nothing left to render on this particular pass through my responses. Because I know if it's not there, then I'm not going to render anything else. So I can take advantage of an early return here. If it is in there, I can say if it's still, for example, I can say if it's still a truthy value, or I could say if it's still a string. And you'll see why I'm saying that in a moment. If it's still a string, then I know it's time to go ahead and render this. So I'll say file names, I'll say responses of file names of I.
Yeah, so what to call this, because this function will call this
the same thing.
thrice.
Responses of file names of I. Now that I've rendered it, I want to leave the entry in there, but I want to mark it as having been rendered. So a simple way of marking it as having been rendered is to change it from being the text to something like false. So the entry is still in the object, which means I'm not going to try to re-add it in there, but I'm not going to try to render it over and over again because it's going to fail this typo check. There's a million different ways that you can choose to implement this logic. I'm just showing you one possible way of saying, I'm looping over this list and I'm checking to see whether I need to render something. At the end of this, if I have rendered all 3 of them, then I can finally output my complete message. This function is going to get called for each of those 3 times.
3 times.
The happy path is that it gets called once with file 1, and then once with file 2, and then once with file 3, and it never needs to get to this early return thing. It never needs to even store anything. But it might get called once with file 3 first, and then once with file 2 first, and then finally the 3rd time with file 1, where it hasn't rendered anything yet. And that 3rd time, when it goes to loop through, it's going to say, I do have a file 1, render it. I do have a file 2, render it. I do have a file 3. So whichever way these come in, I'm always going to render ASAP, but only in the correct articulated order. Yes?
Sorry, maybe I understood the problem statement wrong, but I thought you said you wanted to do it by ordering the callbacks. Or did you not say that?
What do you mean?
So I was thinking just like maybe we would have different callbacks for all the get files, and then somehow we would order them. That's how
we do have different callbacks for all the get files.
Okay, that's fine.
I'm not sure I understand what you mean.
I wasn't expecting this implementation.
Did you solve it a different way?
No, I couldn't.
Okay.
I was thinking more in the lines of promises, but just to order the callbacks in some way, and I couldn't come up with anything.
Well, the only way you're going to end up ordering the callbacks is to have sequential requesting, where you don't even request file 2 until after file 1 is finished, which violates one of the fundamental premises of the setup of the problem, which is to call them in order. That's why that's there, because it's easy if you just want to do serial requesting. But it's the parallel requesting that causes this concurrency coordination to be more complex. Okay? The point that's really being made here is that 3 independent callbacks have to share some closured state, even if it's a global variable. They're going to have to share some closured state to coordinate themselves. That's just, there's no other way around it. Whether it's the global state or whether there's some other wrapper or that variable's passed in. I mean, no matter how you slice it, there's going to have to be some shared variable across all 3 callbacks. And they're going to have to potentially store something in that variable until it's time to come back and get it. That's what we mean by saying that we're coordinating concurrency, is that we're managing that time state complexity. And we can see that there's a solution to it, but I don't think anybody would argue that this is a good, graceful solution to it.
This is a solution to handle. Oh my. Okay, it's because this is a solution to handle is this concurrent. Okay, concurrent response here. So what happened here is that you say, hey, I need to keep track of the response. So far so good in the content. All right, I need to keep track of that. And what? What's next, right? So after I did that, okay, and I need to output that response somehow, which means that because I'm using this hash as a way to store all of this response independently, right? And if I iterate through all of this, and if I iterate through all of this, initially, because I'm hard coding the solution here, because you want to now check if that actually exists as you iterate through that file names. As you iterate through the response, which is a global object that is going to have that. And this global, so this global object response will have now some way to keep track of this. Okay, so we're gonna have the file and the content for all of this. So on each one of those calls, we're not only calling them, and if they don't exist, we're populating is the hash. However, if we want to now get somehow to look at the data, we need to iterate through the data. So one way to iterate through the data is to actually check, right, if the data exists, right? So one way to do that is that, hey, this is now the data that we store here in our response. And if that exists, let me actually print that for that. If not, well, not.
Right? It's ugly, right? But it gets the job done. And I can't tell you many hundreds of times I've solved similar problems in the past where the only tool I had available to me was functions and closured variables. So we can get the job done, even complex scenarios. But this isn't the ideal pattern. And that's why I'm walking you through it. I'm showing you first the pain points that we've been dealing with to motivate why we want better patterns. Is everybody with me on that? Any other questions about exercise 1? We're going to get to come back to the exact same problem domain over and over and over again, okay? You'll get better and better at solving this problem with better patterns.
By the way, I'm not convinced that you're going to return, like if it comes back file 2, file 1, file 3, I think you...
So a simple way of marking it as having been rendered is to change it from being the text to something like false. So the entry is still in the object, which means I'm not going to try to re-add it in there. But I'm not going to try to render it over and over again because it's going to fail this typo check. There's a million different ways that you could choose to implement this logic. I'm just showing you one possible way of saying, I'm looping over this list and I'm checking to see whether I need to render something. At the end of this, if I have rendered all 3 of them, then I can finally output.
So maybe I understood the problem.
Is everybody with me on that? Any other questions about exercise 1? We're going to get to come back to the exact same problem domain over and over and over again, okay? You'll get better and better at solving this problem with better patterns.
By the way, I'm not convinced that you're going to return, like if it comes back file 2, file 1, file 3, I think you might get the complete even after file 2, because won't it fall through?
I'm sorry, what?
Won't you get the complete if it comes back, let's say, file 2, file 1, and then file 3, but after you get file 2, it should print out and fall down through the output complete. And then, so you get a complete, then file 3 should come back, then get another complete.
You're still losing me. Maybe over a break we can
Yeah,
talk
we can
through
do-
it.
yeah.
I mean, you can compare what I've typed here to what I typed in the solution file. The
Oh,
solution
okay.
file is objectively correct, and maybe I missed something, but.
So for example, if you say something like this, and then you run it, and then you take a look now at Chrome, the first text, the middle text, the last text, and complete. That's interesting. I don't know how the things work. Oh, it's because you are breaking that. Not complete. Exactly. If this file doesn't exist, to return false. Yeah. If this file doesn't exist, return false. And this is just as a way to change the response here for being called. Jesus. Okay, this is a lot of the coordination that is required for doing this. All of this is because I don't know how the things work. I mean, the approach here is the approach here. Is the approach here. Is the approach here, because if you don't put here, what it's doing is to try to render all of this.
pretty sure one of those 3 passes is going to hit that thing before it hits the output complete. You're either going to be able to go through the entire for loop, or you're going to hit this case, which stops it from getting to complete. So I've alluded to this already. Let's try to be more articulate about the 2 major problems of callback hell. We saw the symptoms of them. The symptoms of callback hell were that managing that time state complexity was rather awful. It was very manual, it was very hard-coded, hard to do, but there's something deeper even than that. So to try to articulate those 2 problems, I'm going to have to take some conceptual steps back, a little further away from the code. First, I want to talk to you about a principle called inversion of control. By the way, if you do a search for inversion of control, you're going to get lots of different answers in different software domains as to what inversion of control means. So try not to confuse all those different overloaded definitions with the one that I'm going to give you here. What I'm going to give you here is that inversion of control means there's part of my program that I'm in control of executing, and then there's another portion of my code that I'm not in control of executing. And the way that we express that is to take the first half of my program that executes now, and the second half of my code that executes in a callback, and when I give that callback to somebody else, that's what inverts the control, and it puts them in control of when and in what manner to execute the second half of my program.
Inversion of control is when you
when
you pass that callback
I'm going to
function
assert to you that this is one of the
is
2 evils of
responsible
callback
to
hell,
execute that.
this notion of inversion of control. So let's go back to this fundamental set timeout. There's a line 1 and a line 2. Those represent the first half of our program. Lines 3 and 4 represent the second half of our program. We are in control of lines 1 and 2. They're happening now. We are observing them happening now. We are in control of them. Lines 3 and 4 are going to happen at some unspecified later time.
Okay. That'll be all for this video. Take care. Bye-bye.